Okay, so last time we did the Law of Cosines, which basically the Law of Cosines was a step up on the famous Pythagoras theorem. Okay, so an improved version, one that does a little bit more. Today we continue on the same theme. The Law of Sines is, roughly speaking, a law in a similar flavor as the Law of Cosines. It helps you resolve triangles which may be perhaps not right triangles. So it has very similar flavor to the Law of Cosines. A couple things are in order. First, I got to tell you what it says, and second, how to use it. And also, we never really proved the Law of Cosines last time. Today will be a perfect day to settle this. We'll prove both the Law of Sines and Law of Cosines. Okay, any old chump can memorize these things, but it takes a human being to understand them and make sense of the ideas, to really own them. Alright, let's get to it. The Law of Sines. The Law of Sines says if you have a triangle, say some typical triangle like this in flatland, and maybe it's not a right triangle. Here's what you can say about it. It talks about these ratios. So if this angle is A, across from it you find the side that's commonly called A. If this is a B, across from it people usually call this one C, and so on. And the Law of Sines says something special about these ratios. It says that sine of A is to A. Sine of A is to A. That's these two quantities here. Sine of A is to A, this ratio, as sine of B is to little b, as this ratio, sine of B is to little b. That's exactly what the Law of Sines says, and it also applies. And that, you know, you can look at it from, you can compare any of the ratios. All three ratios are the same, meaning that you could also say both of these are also equal to the ratio sine of C to little c. That's what the Law of Sines says, and exactly how this helps you solve triangles is the same way that the Law of Cosines does. If you can look at this ratio, which involves these two variables, and this ratio, which involves these two variables, that involves four quantities. If you know three of them, and one of them is unknown, the Law of Sines would help you figure it out. Does that make sense? That's why it's very similar to the Law of Cosines, and it'll help you solve triangles. Exactly the same is true as before. There may be four possibilities. There may be no real solutions, one, two, or infinite. Okay, so let's try our Law of Sines on this nice triangle. Here's a strategy. You pair up ratios that you know. You say to yourself, I know this ratio. I know the 70 and the 5, and you want to pair it up with the one where you only know one of the quantities. For example, the A and the 4. Out of these four quantities, only one is not known. That would be a perfect candidate. So you'd go something like this. You say to yourself, you know what? Sine of A is to 4. That's this pairing. Sine of A is to 4 as sine of 70 is to 5. And that gives you an equation with just one known. A piece of cake to solve. So you'd multiply both sides by 4 and you get that sine of A is equal to 4 over 5 times sine of 70 degrees. Okay. And then you'd get your magic number machine here. Where is it? Where is it? Let's bring it up. Hello, little number machine. There you are. And we compute 4 divided by 5 times sine of 70 degrees, and you get that that's 0.75 approximately. So this gives you that sine of A is approximately 0.75. From there you solve the equation the way you were with practice. That gives you the solutions there, solutions there. The first one can be obtained by doing a little sine inverse. So you do copy sine inverse of, let me see the computation we just did, and that gives you about 48 degrees for the first one. So this is 48 degrees, actually I'll be a little bit more precise, 48.8 degrees. So in this case A is 48, or there's another possibility, maybe A is equal to this. To get that one, you'd go, you'd think, alright, from here to here is 48, that means from here to here is also 48. So you take 180, from 180 degrees, come back 48. That would give you approximately 131.2. So 131.2. So your candidates are A is equal to 48.8 degrees, or 131.2 degrees, or a bunch of other candidates that are way over here, or way over here that don't make sense because A is supposed to be an interior angle of a triangle. So it's got to be either 48 or 131. But wait a minute, if it's 131, these two angles already add up to more than 180. See, if this was 131 plus 70, that'd be 210. That's not happening. And so you say to yourself, you know what? This one is not happening, so therefore my only candidate is A has to be 48.8 degrees. And so you rack that one, 48.8 degrees. And you say to yourself, you know what? This one's almost there. Now here's what we have. Let's get rid of this for now. And let's go back to the drawing board. All that work was just so we could get A. And now we've got A. Look at how many items we now know. We know these two angles. Wait a minute, we can figure that angle as well because they have to add up to 180. So you can say to yourself, you know what? If I take my 180 and I subtract the 48.8 and then I subtract the 70, that leaves me with 61.2. So this angle has to be 61.2 degrees. There you go. Almost all items are known. One more thing left to figure out, B. So you can again use the law of cosines or the law of sines. Let's just practice law of sines. You could say B is to sine of 61.2 degrees. Here we go again. Now I'm using this ratio. I'm saying B is to sine of 61 degrees as I could use any other ratios. Let me use this ratio. So I'll say B is to sine of 61 degrees as 5 is to sine of 70 degrees. There you go. How many unknowns do you have in this equation? Only one, B. So therefore you get that B is equal to sine of 61.2 degrees times 5 divided by sine of 70 degrees. And let's see. Just run some numbers here. Run some numbers and you should be good to go. I'll go like this. I'll go sine of, first of all I'll clear everything, and I'll go sine of 61.5. Nope. I'll go sine of 61.2 times 5 divided by sine of 70 degrees. And that gives me approximately 4.66. So therefore my B is approximately 4.66. And having done that, 4.66, I've got the triangle. Everything is resolved. Okay? You know, this is a case where there's exactly one solution. I thought it'd be fun to try to do a problem that we previously did using the law of cosines, but this time solve it using the law of sines, just for fun. You guys remember this problem, the one that had exactly two solutions, where we applied the law of cosines involving these four quantities, of which all of them we knew except for B. Applied the law of cosines, got a quadratic equation, solved it. I think I had an error here. I had 8 point something last time. I cleaned it up. We got two solutions for B. B is about 4.72. Can you see it? And B is about 14.3. And what the reason for that is that this angle over here is kind of, this side is ambiguous. Anything could happen over here, so this side could be as it is now, this way, or it could be this way. Now it was giving us two different values of B, because this one has two solutions. So I thought it'd be fun to try exactly the same problem, but this time we try it with the law of sines. So here's the proposition. Let's forget about all this stuff Forget about that, 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 and start all over. Forget about this, forget about that. Now we start fresh from the law of sines, and so we say to ourselves, hey, we got this. We say to ourselves, sine of A. See, I'm going for this ratio right here. This ratio. Sine of A is to 10s. I'll compare it to this ratio, the ratio I know. Sine of 20 is to 6. Okay. Sine of 20 is to 6 as sine of A is to 10. And look at, count them, how many unknowns you have from these four. Only one unknown. Therefore, it's a duck soup. Sine of A would be equal to 10 over 6 times sine of 20 degrees. Now time for a little calculator. So we go like this. Clear everything. 10 divided by 6 times sine of 20. That gives you approximately 0.57. So sine of A is approximately 0.57. Then that's a simple equation. We solve it using the standard techniques. This is sine. This is 0.57. So you've got a solution there. You've got a solution there. The first one we can get by doing a little sine inverse. So we clear this and we go sine inverse, and we take the last guy that we did that, and it gives us that's about 34.7 degrees. So this is about 34.7. I'll go 34.8 degrees. That would put this one over here at 180. Come back 34.8. So I'll subtract that from 180. That gives me about 145.2 degrees. So there are many more solutions, but none of them make sense if they're interior angles of a right triangle. However, both of these make sense. If that would fit fairly well there, that would give you only 30 or 54.8 degrees, which would leave plenty for B. This one would fit there too. That would be 160. So this gives us the two possibilities. A is equal to approximately 34.8 degrees or 145.2 degrees. Two completely viable options. As promised, that means that we have both of these options where A is really little, it's about 34 degrees, or A is really big, it's about 140 degrees. Those are exactly the two possibilities. The ones that we were coming up before when we solved the quadratic equation for B. So let's finish it off. Let me see, where were we? Not there. So one of them was 34 degrees. So let's do this one. This one was 34.8 degrees. And how would you finish it off? Well, here's one way you could finish it off. You could say, oh, by the way, if this is 30 and this is 34.8, we know exactly how much that is up there. You take 180 and then you subtract this 20, and then you subtract this 34.8, and that leaves you with 125.2 degrees. And now we're cooking. Now we say something like this. We'll play this game. B is to sine of 125.2 degrees. That is, I'm comparing this ratio right here. B is to sine of this as, I'll compare it to this ratio. 6 is to sine of 20 degrees. 6 is to sine of 20 degrees, as B is to sine of 125. Then you multiply both sides by this denominator, so that would give you a sine of 125.2 degrees times 6 over sine of 20 degrees. That would be equal to B, approximately. So then you come back with your little calculator, and let's do it. Clear everything, and you go sine of 125.2 times 6 divided by sine of 20, that's equal to about 14.3. B is equal to about 14.3, which is an expected result. If you remember, that's exactly what we got using the law of cosines. I told you. That's why they pay me. So that triangle is completely resolved. Then we go on to the other one. The other one was the case when this one was 100 and what was it? 145.2. Yeah. So this was 145.2, and that would make this one. Let me see. To that one, I'm going to add that's plus 180. That makes this one about 14.8 degrees. Okay, and now we're cooking. Guess what? I'm going to play this game. B is to sine of 14.8 degrees. That is, I'm comparing this ratio. B is to sine of 14 degrees. As I'll compare it to this ratio. As 6 is to sine of 20 degrees. Look at that. How many unknowns here? 1, I told you. So therefore, B is equal to 6 over sine of 20 degrees times my sine of 14.8 degrees, which is easy. I'll go like this, clear everything. I'll go 6 divided by sine of 20 times sine of 14.8. It's approximately 4.48. I told you, it should be really close to the previous answer that we got using the law of cosines. Really, really nice examples. There's nothing to memorize. You just solve the equations correctly. Law of sines. Perfect. It tells you about these ratios of opposite side, how the ratios of sine of one angle compared to the opposite side is the same for all the corners. Okay? That leaves only one thing left to do, my friends. One thing and one thing only. And that is to settle why. Why is it true? Where did this come from? Not only this one, the law of sines, but the law of cosines. Where did that come from? You remember? You remember? Where does this come from? The stuff about generalizing the Pythagorean theorem. That's some crazy stuff. That's some gangster stuff. Alright, so now it's time to settle why. Why? Let's prove this one first. You know that it really doesn't matter which, there's three ratios here, but it really doesn't matter which one you prove first. As long as you prove two of them, the proof for the other two will be identical. So if we can just get this far, we'll be in good shape. You can see how the proof goes. Here's the idea for the proof. First of all, this is the end game. This is the object. Okay. This right here is the object. This is the end. And here. This is the start. This is the start. You can start with this, and you have to take logical steps, logical steps, logical steps, until we deliver the goods. So we take you to the promised land right here. If we can do that in a nice, convincing way, then we've got ourselves a nice proof. This is why they pay me. Insane amounts of money. So first, watch this idea. You drop a perpendicular there, so that this is perpendicular. And you call this side something. You call it anything you want. I could call it hair if I want. Okay? That's right, I just called it hair. So then here's what happens. Look at this. Sine of A. What is the definition of sine? Sine is a ratio of opposite to hypotenuse. So forget about this triangle. I'm just looking at that right triangle right there. The sine of A's definition opposite to hypotenuse. So that would be the hair over the B. Yes? On the other hand, if I cover this and I look at sine of B, sine of B is defined as a ratio of opposite to hypotenuse. So this would be hair over A. That means that the hair is equal to A times sine of B. But this hair is exactly the same hair as that hair. By the way, it's kind of silly. You could call it Y, X, T, lambda. You could call it anything you want. I'm just calling it hair for fun. But this would be b sine of a is equal to hair. But wait a minute, how is this hair compared to that hair? Well, they're actually the same line. This triangle and that triangle share exactly the same side, so this is exactly the same. Therefore, these two have to be equal to each other. This one has to be equal to that one. They are the same hair. That would tell you that b sine of a is equal to a sine of b. Yes? Which would later lead you to conclude that, hey, maybe you could divide both sides by BA, divide both sides by BA, so that you just clean up, I want the A only up there. That here you can cancel the B and the B, here you can cancel the A and the A. And that would leave you with, oh no we didn't, that would leave you with sine of B over B. I told you. Call me the mailman. Because I deliver, huh, Diego? That's right. There it is. That's the proof of the law of sines. For these ratios anyways. You could just turn a triangle now and do it for B and C and you've got a complete proof. Okay? More or less. You might need some minor adjustments, but that's the spirit of the proof. And that leaves one thing only left to do. The law of cosines. Okay, now let's see the proof of the law of cosines. This is what we start off with. We start off with a standard triangle here. And from there we got to take logical steps, perfection, beauty, and creativity and reasoning like you've never seen before until we can deliver the goods, until we can deliver the law of cosines. Okay, if we can do that in a convincing way, then we would call that a great proof. And there are many ways to do it. Here's one way to do it. You make note of this point right here and you try to figure out its coordinates. You could figure out its coordinates by something that we did before when we did the law of, when we proved the mother of them all. We remember this is very easy to find the coordinates for. This would be b cosine of a and b sine of a. That's based on this triangle here, but just ignoring that part. The x would be b cosine a, the y would be b sine a. The coordinates for this one would be c comma 0. This distance here is c, and that's what would make that point c comma 0. Now the key in the proof, amazingly enough, we've seen this before, such a small creative idea, is to look at that area A, in that distance A, in two different ways. We look at it first as what it is, just a square. So on the one hand we have a square, but on the other hand it's equal to, and then I'll emphasize this, there's a green way of looking at it, where we look at that point and use the distance formula. The distance formula says that I could call this d square. D square is equal to c minus b cosine a squared plus 0 minus b sine a quantity squared. Right? That's just a distance formula applied to these two points using the coordinates. You get that? And at first it looks really ugly, but then you can clean it up. If you clean it up, you get that d squared is equal to c squared minus 2cb cosine a plus b squared sine square a. Right? That's just foiling this, cleaning that up, and that's what you get. Plus, let me backtrack. I know you guys probably want to see that again, so I'll do it again for you guys. C squared, I'm just kidding, it's for me, 2cb cosine a plus b squared cosine a, that's the three terms from the FOIL, plus b squared sine square a. You see that? There you go. But this cleans up nicely. Look at this, a cosine square a and a sine square a. What do these two turn into? You could factor out the b squared. This would be d squared is equal to c squared minus 2cb cosine a plus b squared, and I can factor out a cosine square a plus a sine square a. And what is this equal to? Every time you can you have a sine square A and a cosine square A, you can go to the exchange house and exchange them for a 1. So this becomes d squared is equal to c squared minus 2cb cosine A plus what? Plus b squared. Or if you clean it up, the d squared is equal to b squared plus c squared minus 2cb cosine A. But on the other hand, that d squared is also equal to a squared. A squared is equal to d squared because they're exactly the same line. So therefore, a squared is equal to b squared plus c squared minus 2cb cosine A. My friends, what we have here is exactly the result we wanted. It's so simple. It's just looking at this distance two different ways. One way is just a squared, the other way using the distance formula, and you're done. As easy as it sounds, that's all you gotta do.